Let's start with the first order system. Let's assume that we have a first order system which is governed by the following transfer function. So let's assume the transfer function of the system is Gp of s equal to y of s upon x of s, where y of s is the output in the S domain, x is the input in the S domain, and Gp of s is the transfer function for the system. And let's assume that we have a first order system which have the transfer function Kp tau s plus 1. Let's say this is equation number 1. So let's assume that we have given a sinusoidal input to the process as described by the equation number 1. And here we have to find out the output of the process at the steady state or when t tends to infinity. So let's begin the problem. So since we have given a sinusoidal input to the process, so here we have a model of process which is having a transfer function of Kp tau s plus 1, and this is the transfer function of Gp of s, and here we have output of the system in S domain, that is y of s, and here we have input of the system in the S domain x of s. So the transfer function of a process relates the output to the input in the S domain, right? So here we have given, let's say the input in time domain is given as, where xt is the derivation variable. So xt, capital XT is the derivation of input variable. And this derivation can be written in small x of t minus x at the steady state. So x subscript double s is the steady state value of the input, and this is governed by a sinusoidal input. So let's say the sinusoidal input we are giving here is sine omega t. So let's say capital X of t is a sine omega t, where a is the magnitude of the sine wave and omega is the angular frequency of the sine wave. So this is the equation number 2. So now take the Laplace transform. So taking the Laplace transform, taking the Laplace transform of 2, equation number 2, we will get x of s equal to Laplace transform of a times sine omega t, and a is the magnitude, which is a constant, so we can take a outside, and the Laplace transform of sine omega t is omega upon s square plus omega square. So this is the equation number 3. So now from equation number 1, we can write y of s equal to x of s into gp of s, right? So from equation number 1, we can write y of s equal to x of s times gp of s, and this will be a omega times gp of s. So a omega upon s square plus omega square, and then we have kp upon tau s plus 1. So this is the y of s, the output in s domain, right? So before solving this expression, by taking the inverse Laplace transform, we have to do partial expansion of this y of s. So in the denominator we have tau s plus 1, and here the coefficient of s is tau. So to make the coefficient of s as unity, we have to divide tau s plus 1 by tau, and similarly we have to also divide kp by tau. So to make the coefficient of s unity, divide the numerator and denominator by tau. So finally we can write y of s equal to jp a omega by tau upon s square plus omega square and then s plus 1 by tau. So in the denominator we have one second degree polynomial in the form of a square plus b square. So this can be written into two first order first degree factor in S. So using this formula, using a square plus b square equal to a square minus b square, a square minus j b square, and finally this can be written as a minus jb a plus jb. So using this formula, the s square plus omega square can be written in the similar way. So finally we will get y of s equal to, let's say the numerator equal to k1, and in the denominator we will have s minus j omega s plus j omega and then s plus 1 by tau. So this is the equation number 4. So now this expression can be written in the partial fraction expansion form. So here we will use c1 by s plus 1 by tau as the first term, c2 by s minus j omega second term plus c3 s plus j omega, and this is fifth, and this is y of s. So to find out these unknowns C1, C2, C3, we will use the shortcut method. So to calculate C1, we have to use limit s tends to minus 1 by tau as the denominator of first term, the denominator of C1, that is s plus 1 by tau multiplied with y of s, and y of s is given by equation number 4. So finally here we will get k1 upon s square plus omega square and s equal to minus 1 by tau. So we will get k1 upon minus 1 by tau whole square plus omega square, and this will give us k1 tau square 1 plus omega square tau square, and this is the equation number 6. Similarly, C2 can be evaluated the similar way. So limit s tends to j omega and the denominator of C2, that is s minus j omega times y of s. So from equation number 4 we have y of s equal to k1 upon s minus j omega into s plus j omega into s plus 1 by tau, and which will be multiplied with s minus j omega. So s minus j omega both will cancel out and we will left with k upon, so we will be left with k 1 upon s plus j omega and s plus 1 by tau, and here we have to put s is equal to j omega. So once we put s is equal to j omega, we will get k1 to j omega. From the second term we will get 1 upon tau plus j omega, and this can be written as k1 upon 2 j omega take 1 by tau common, so we will having 1 plus j omega tau. So finally we will get k1 tau upon 2j omega and 1 plus j omega tau. So the conjugate of first term in the denominator is minus 2j omega. So we have to multiply with minus 2j omega and divide by minus 2j omega. Similarly, the conjugate of second factor 1 plus j omega tau is 1 minus j omega tau. So we have to multiply with 1 minus j omega tau and 1 minus j omega tau. So using the complex number analysis, so let's say we have a complex number z1 equal to a plus jb, and the conjugate of z1 is a minus jb. So z1 into the complex of z1, that is z1 var equal to a plus jb times a minus jb, and this can be written as a square minus jb whole square, and this can be written as a square minus b square, and this will be a square plus b square, which is the magnitude of z1. So since we are multiplying the denominator term by its conjugate, so in the denominator we will have the magnitude square, so C2 will be, so using this formula we will get C2 will be equal to K1 tau upon, so 2j omega into minus 2j omega, so we will get b square, a square plus b square, a is 0, so we will have 0 square plus 2 omega square. Similarly, in the second term we will have 1 square plus omega tau whole square, and in the numerator we will have So minus 2j omega. So take minus sign out. So we will have 2j omega. So minus minus plus, and then we will have plus, and this will be minus 2j omega into j omega tau. So this will be minus j square. So minus into minus 1 plus 1, and we have omega square tau. So this is omega square tau. And 2. So finally we will be having two omega common, and then we having omega tau plus j k1 times tau with negative sign, and here we will be having 2 to the 4 omega square and 1 plus omega square tau square. So finally C2 is, so this omega, 1 omega gone, and 2 2. So we will be having minus k1 tau upon 2 omega 1 plus omega square tau square, and here omega tau plus j. So this is 7. So we have C2 equal to this. So C2 is a complex number. Similarly, we can find C3 as limit s tends to minus j omega s plus j omega times y of s, and this will be the complex conjugate of C2. Since C2 is a complex number, so we will get the complex conjugate of C2, and that is minus k1 tau omega tau minus j upon 2 omega 1 plus omega square tau square, and this will be C3, and this is question number 8. So this you can prove that C3 is the complex conjugate of C2. So hence Now substituting the value of C1, C2 and C3 in equation 5. So we will get y of s equal to C1, and C1 is k tau square. So C1 is k1 tau square 1 plus omega square tau square. This is the, and 1 upon s plus 1 by tau. So this is the first term. The next term is C2. So the next term is C2 upon s minus j omega. So from equation number 5 we can see the second term is C2 upon s minus j omega, and the third term is C3 upon s plus j omega. So the value of C2 is minus k1 tau. This is minus k1 tau, and then omega tau plus j upon 2 omega, and then we have 1 plus omega square tau square, and then we have 1 upon s minus j omega. Similarly, we have the third term C3 upon s plus j omega, and C3 is the complex conjugate of C2, and C2 is k1 tau omega tau plus j, and since it's a complex conjugate, so we will use minus j upon 2 omega 1 plus omega square tau square, and here we will have 1 upon s plus j omega. So this is equation number. So we can further simplify this. So in the denominator we have this common term, that is 1 plus omega square tau square, and in the numerator we have k1 tau. So we can take this k1 tau common, and 1 plus omega square tau square common, and we will put the other terms inside the bracket. So the first term will be tau 1 upon s plus 1 by tau. The second term will be minus, so this will be omega tau minus plus j upon 2 omega and 1 upon s minus j omega, and then we have minus omega tau minus j upon 2 omega 1 upon s plus j omega. So this is equation number 9, right? So after simplification we have equation 9, and this is y of s. So now taking the inverse Laplace of equation 9. So taking inverse Laplace transform of equation 9. So we will get in the left hand side the inverse Laplace of y of s will be y of t equal to k1 tau upon 1 plus omega square tau square, and then in the denominator, inside the bracket we will have the other term. So the first term, so the inverse Laplace of the first term, so this will become tau, the exponential term, e to the power minus t upon tau. Then we have minus omega tau plus j upon 2 omega e to the power minus omega t. So the second term will be minus omega tau plus j upon 2 omega e to the power plus j omega t. Then we will have third term minus omega tau minus j upon 2 omega e to the power minus j omega t. Since we know that e to the power j omega t will be equal to cos omega t plus j sin omega t. E to the power minus j omega t will be equal to cos omega t minus j sin omega t. So e to the power j omega t plus e to the power minus j omega t will give you to real part of this. Real part of e to the power j omega t, and that is twice of cos omega t. Similarly, e to the power j omega t minus e to the power minus j omega t will give us two imaginary part of e to the power j omega t, and that will be 2 j sin omega t. So if we further simplify y of t, we can express yt as follows. So we can write y of t equal to k1 tau 1 plus omega square tau square, right? Or in the bracket we will have tau e to the power minus t upon tau, the first term. Then we will have minus, so omega tau by 2 omega we can take common, so omega tau by 2 omega common, e to the power j omega tau and plus e to the power minus j omega t, so plus e to the power minus j omega t, and then we will have 1 upon 2 omega with negative sign, so 1 upon 2 omega as a common, and e to the power so basically this is not 1 by 2 omega, it's a j by 2 omega, and then we have in the second bracket e to the power j omega tau j omega t minus e to the power minus j omega t. So we can write this whole term as So y of t, we can write y of t equal to, so we can copy this whole expression as it is, copy and then paste. So we can put here, hit enter. Now we can replace this term, exponential term. So this exponential term we can replace, and this exponential term we can replace, right? So if you see here, so e to the power j omega t, so this e to the power j omega t plus e to the power minus j omega t equal to 2 cos omega t. So I can write this 2 cos omega t, and in the second bracket e to the power j omega t minus e to the power minus j omega t, I can write 2j sine omega t. So finally we can copy this whole expression as it is, and now put here, hit enter, and then after simplification, if you see here, so this 2 cancel out, omega cancel out, here this 2 cancel out, right? So finally what we will get here in the second term, here we will have only this tau term, and here we will have j omega term, right? So further simplifying, we will get k1 tau upon 1 plus omega square tau square, then tau e to the power minus t upon tau minus tau cos omega t, so minus j square, and j square is minus 1, so we will have plus 1 by omega sine omega t. And this further can be simplified as k1 tau 1 plus omega square tau square. The first term will remain as it is, e to the power minus t upon tau, and the second term can be written in this form, right? R sine omega t plus phi. So basically we have y of t equal to this expression, equation 10, right? So let's say this is the equation 10 and this is equation 11, right? So from 10 equation 10, the ultimate response, the ultimate response of first order system y infinity can be written as T1 tau upon 1 plus omega square tau square upon tau e to the power minus infinity, and then we will have minus tau cos omega t plus 1 by omega sin omega t. So this term will be 0. So finally we will have T1 tau upon 1 plus omega square tau square, and then this minus tau cos omega t plus 1 upon omega sin omega t, right? And this can be written as r sin omega t plus phi. And this is r. So this where r square will be so let's say this is p square plus q square, right? And this is p and this is q. So minus tau square plus 1 by omega square, and then we will have omega square tau square plus 1 upon omega square. So this is the r square, and then we have phi. So phi can be written as 10 phi equal to E upon Q, and P is minus tau 1 upon omega, and this will be minus omega tau. So phi will be tan inverse minus omega tau. And this given, so this given is Kp with omega upon tau, right? So finally, what we need to find out, therefore the final expression, therefore the final expression for phi infinity can be written as V1 tau upon 1 plus omega square tau square. Into omega square tau square plus 1 under root upon omega. This is the value of r, and then we have sine omega t plus phi. So this is the final steady state response for the first order system with a sinusoidal input. So further simplifying, we will get, so putting the value of k 1, that is kp a omega upon tau, and here we have 1 plus omega square tau square under root 1 plus omega square tau square sine omega t plus phi. So now this omega get cancelled, tau get cancelled. So finally we will get kp a upon under root 1 plus omega square tau square, and then sine omega t plus phi. So this is the ultimate steady state response of a sinusoidal input to the first order system, and this will be the equation number 12, right? So the amplitude of the output will be this bracket term. So let's say this is capital A1 and this is sine omega t plus phi. So here we can see from the first slide, right? For the first order system, so I will just copy this portion, copy, and then finally we can conclude here that for the first order system, so I can conclude that for the first order system, if we have a sinusoidal input A omega so x of t, capital X of t is, let's say, A sine omega t, right? So this is, let's say, we have input, so the output will be also a sinusoidal input with the amplitude of A1 sine omega t plus a phase angle of phi, right? And this amplitude is given by, and this amplitude will be given by A kp upon under root 1 plus omega square and tau square, and this is, let's say, equation number 14, right? Sorry, equation number 13. So this is equation number 13, and the phase angle is tan inverse minus omega tau, and this is equation number 14. This is for the first order system, right? For the second order system it will be different, but again it will, for the second order it will also give you the sinusoidal input, right? So here we have to define two terms. One is amplitude ratio, amplitude ratio, right? That is AR, and this amplitude ratio is defined as the ratio of output amplitude. So amplitude ratio is defined as the amplitude of output to the amplitude of input, right? So we have already seen that for a sinusoidal input we will also have a sinusoidal output, and if the output response will have the amplitude of A1 and the input having the amplitude of A, so the ratio A1 to A will give you the amplitude ratio, right? And from the equation number 13, for the first order system, the amplitude ratio will be Kp upon under root 1 plus omega square and tau square, right? So this will be the amplitude